Okay, now we're going to take a closer look at existence and uniqueness with row reduced echelon form. So in the last video, we introduced row reduced echelon form. Now we're going to talk about how you can understand existence and uniqueness in more detail using row reduced echelon form. Okay, so we have this theorem that states a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has a row of the form, and then you see in matrix notation you have a 0, and then, for however many columns before B, you have zeros, and then B. So B is non-zero in this case too. Okay, so what's a pivot column? In the last video, we introduced pivot columns as a column that has a pivot position. And so a pivot position that indicates that you have a pivot column is the leftmost leading entry of your row. So echelon form has a step-like pattern. So say we have the first element or the first entry in row 1. So the leftmost entry of row 1, we want a 1 for reduced echelon form, and then zeros under that in every other row for that column. And then in the next one, in the next column, we want the second entry in row 2. We want everything under that to be 0. And then we want that to go in a step-like pattern. So each step, each leftmost leading one with zeros under it, that's going to be a pivot position. So the corresponding column for that is going to be a pivot column. And here, bringing it back to the main topic, we want to know whether a linear system is consistent. So we want to know if it has a solution. So this theorem is telling us that the system has a solution if the rightmost column of the augmented matrix is not a pivot column. Okay, now we're going to go to the second main section of text. If a linear system is consistent, then the solution set contains either a unique solution when there are no free variables, or infinitely many solutions when there is at least one free variable. So we have a matrix here with row 1 entries as 1, 6, 2, -5, -2, -4, row 2, 0, 0, 2, -8, -1, 3, row 3, 0, 0, 0, 0, 1, 7. And the matrix is in echelon form, but not reduced echelon form. So we should now find a row equivalent reduced echelon form matrix to solve for the basic variables. And this is basically another warm-up from the last video, because we did the same thing in the last example in the previous video that introduces row reduced echelon form. Okay, so we can do this with the aforementioned matrix by adding row 3 to row 2. And then we want to do -2 times row 2, and we want to add that to row 1. And we're going to have for the first row 1, 6, 0, 3, 0, 0, and then row 2, 0, 0, 1, -4, 0, 5, row 3, 0, 0, 0, 0, 1, 7. In the form of a system of linear equations, the first row is going to be x1 plus 6x2 plus 3x4 equals 0. And the second row is x3 minus 4x4 equals 5. And then in the third row, we just have x5 equals 7. Okay, so looking at our system, we have 1, 2, 3, 4, 5 variables. We have 5 variables, but we only have 1, 2, 3. We've got 3 pivot positions. We got 3 pivot columns. And this tells us we're going to have as many basic variables as there are pivot columns. And for the rest of them, we're going to have free variables. So we're going to write the general solution. We're going to write that in terms of the free variables. So we have x1 equals -6x2 minus 3x4. x2 is free. x3 equals 4. x4 plus 5. x4 is free. And then x5 equals 7. And now that we've got a warm-up in, so now that we're familiar with the procedure for finding the basic variables, what can we say about the existence and uniqueness of the solutions to the system of equations? And to answer that question, we're going to start out with a whole new system. So we have in the first row 3x2 minus 6x3 plus 6x4 plus 4x5 is equal to -5. Second row, 3x1 minus 7x2 plus 8x3 minus 5x4 plus 8x5 is equal to 9. Third row, 3x1 minus 9x2 plus 12x3 minus 9x4 plus 6x5 equals 15. And we already went over the procedure for getting to reduced echelon form. So I'm not going to make you do that again. So let's just look here at the system of linear equations that I've written out, and let's look at it in echelon form below. So in echelon form, already the row reduction's already been done. We have for the first row, we have 3, -9, 12, -9, 6, 15, then 0, 2, -4, 4, 2, -6. Then the third row, 0, 0, 0, 0, 1, 4. Okay, and looking at this system in the context of the beginning of the video where I stated a theorem, from the theorem, the rightmost column is not a pivot column. You can look at the system of equations and then look at the matrix that we have in echelon form, and you can see that the rightmost column is not a pivot column. So we know the system has a solution and it's consistent. So the existence of a solution is clear, but the free variables indicate that there are infinitely many solutions, or in other words, the system is not unique. And this is going to conclude the videos on echelon forms and how to row reduce to get into echelon form. In the next videos, we're going to be talking about vector equations.